Okay, good afternoon. So last time we talked about introduction to duality, and using an example, we saw how to convert a primal problem into a dual problem. So just to refresh your memory, it's always good to have a primal problem in the form of maximize and the constraints in the form of less than equal to. Okay, when we have this very easily can be transformed into its dual, where we have seen that doing so would give us this as our dual, right? So our less than equal to would obviously become greater than equal to, and our maximize would become minimize. Our objective functions would become the right-hand side vector. That means would be on the right-hand side of the constraints, the coefficients, and the coefficients on the right-hand side of the constraints in the primal would become our objective function. So for this very simple example, we saw that we could convert it into dual, and the steps to do that is, so this is very important, keep this in mind. So every primal problem can be written in this dual form. That means any LPP problem that is given to you always has a dual. Okay, it's not that there exists no dual for it. There always exists a dual for an LPP problem. If the primal is a maximization problem, its dual will always be minimization. If the primal is minimization, the dual will be a maximization. So they are always the opposite. If the constraints in the prime are less than equal to, then in its dual, it will be greater than equal to, okay? Greater than and equal to, okay? So if the primal has n constraints, okay, so this is very important. Item number 4 is very important. If the primal has n constraints and let's say m variables, then its dual will just have the opposite. That means it will have m constraints and n variables. Okay, so keep that in mind. And the fifth point I told you, the left-hand side of the constraints in the primal will become the objective function of the dual and vice versa. And of course, the coefficient matrix, which is formed from the constraints, the coefficients of the constraints in the primal will be the transpose of that in the dual. So if you want to write it in the matrix form, we would see that the primal would be maximized some objective function subject to less than equal to, where the variables are greater than equal to, and its dual would be minimized the right-hand side of the constraint, which is B, as you see it comes over here, subject to A transpose. That I told you, this coefficient matrix would be the transpose in the dual, greater than equal to C, and this C is the objective function in the prime. Okay, so as I told you, this was a very simple example where everything was in a perfect world would be just maximize and less than equal to form, but it's not the case always. We may have LPP problems where the objective function may not be a maximize, it may be minimized. The constraints may not always be less than equal to. You can have equality, greater than equal to, and the variables also may not always be greater than equal to, as we see over here. It can also be less than equal to, or it can be unrestricted in sign. That means it could even take negative values, 0, or even positive values. So we have to even know how to deal with such LPP problems, okay? Now, to do that, let's have a more general case example, I would say. Let's call it problem A.1, where we look at all these cases and we see how we can solve it, okay? So what we have is, now we have an LPP over here. Let me get my pen ready. We have an LPP over here, okay, where we see it's minimize some objective function. And in our constraints, we have the equality. We have greater than equal to, we have less than equal to, which we have already dealt with before. And again, we have a greater than equal to. And you see over here, we have greater than equal to variable, unrestricted variable, and less than equal to variable. So we are trying to cover all these 3 cases that we have mentioned over here and see how we can obtain the dual for this guy. Okay? Any questions so far?
No.
Well, I think I should interrupt and ask some questions in between, because I feel like you guys, some of you log in and just disappear, and I'm just talking to very few people. Okay, so let's begin. The first thing, well, as you see over here, I decided to begin with variable x2. Because this unrestricted, frankly speaking, always irritates me a lot. Okay, so I try to get rid of this unrestricted thing as soon as possible. So I look at variable 2 in my primal, and in variable 2, I'm sorry, I look at x2, which is my second decision variable in the primal, and it's unrestricted. So what has to happen is that it should always be greater than equal to 0, right? So as we have studied earlier, in order to get rid of this problem, what we do is we introduce two new decision variables of okay, I've written it over here. So what we do is we define two variables, x4 and x5, and the difference of this is actually equal to x2. Okay, so x4, if I define x4 and x5 to be some non-negative variable values, okay, that some non-negative variables that non-negative variables, then I can say that x2 was equal to x4 minus x5. Okay, and by doing that, so I can replace it by, so I replace x2 by x4 and x5. And another thing is about the x3. Well, x3 is also less than equal to 0, which is not what we want. So we should have x3 greater than or equal to 0. So we know to do that, you just multiply both sides by -1. And therefore, instead, I would define some x6 is equal to minus x3. Okay, so I just multiply, so I define x3, x6. Well, just multiplying both sides. So now basically what I've done is I've said that x3 is equal to minus x6, doesn't matter. Okay, so then I define the new variable x6 to replace minus x3. Okay, and that would be greater than equal to 0. So does everyone understand how I get rid of this problem and this problem? Any questions?
Not yet.
Okay, let me just give Ainur. Ainur, please let these students in. I've already let them. So if anyone else joins, just let them in. Thank you.
Okay.
Okay. So if this is clear, let's move on. So we got rid of this problem, and now, so if we rewrite our primal, I call it a.2, it would look something like this. Okay. Let me move this so I can also see what I'm talking about. Okay, good. So what happened is, instead of x2, I replaced it with x3 and x4 and x5, because we have x3 or x4 and x5. So you see we have 5 times x4 minus x5, 2 times x4 minus x5, 5 times x4 minus x5. So I've replaced it. So I have x4, x5 greater than equal to 0. And in place of x3, I have written what? Minus x6. So instead of x3, you write minus 4x6, and you just replace it, and x6 will be greater than equal to 0. So we got rid of this problem. Okay, now let's look at what's the next thing to solve. Okay, so the next thing that I did is I changed the maximize to, I've changed the objective function to a maximization problem. Over here, it was minimize. We have to write it as maximize, right? Because I told you that's more desirable when you want to find the dual. So always try to convert the objective function to maximize, and all the constraints to less than equal to form. Okay, from there, converting to dual is very straightforward. Okay, but again, I will show you in the end a technique where you do not have to do any of that. By just looking at the primal, you can just write, there are some sets of rules, and you can just convert it into dual without having to make this conversion from any primal to standard form and then standard form to dual. Okay, we'll look at that. But to understand that, we have to go through the details using this example so you understand it better. Okay, so to maximize this guy, what we do is we write maximize and you put a minus in front of the whole thing. That's what I did over here. So now this is my objective function, which is multiplied by -1. The next thing is now the first constraint, which is the equal to constraint. Okay, so look at this constraint. This constraint, which I have numbered as 5, this guy. Okay, you see that there's an equality sign. I have to change this to less than equal to, right? So how do I do that? Let me ask you. Who's going to answer? How do I change this constraint into a less than equal to constraint?
Introduce a new variable.
Could you, my microphone. Can you speak loudly, please?
Introduce a new variable.
Introduce a new variable. So you guys are not studying.
We need to change left, right hand side.
Equality. It is the same as saying this and this together. Am I right?
Yes.
I can replace equality with greater than equal to or less than equal to. We have already seen this previously, guys. Don't disappoint me, please. Okay. So what we do is when you have an equality sign, we want to write it in the form of less than equal to. So what you do is first you convert it into a form where it becomes inequality. And the only way to do that is to write it in the form of two constraints, one with less than equal to sign and the other with greater than equal to sign. Is it clear, guys?
Yes.
Okay, so you see, that's what I did over here. I wrote it in terms of less than equal to 12, okay? So if you look at this, so this is equal to 12. So I write less than equal to 12, and the other one would be greater than equal to 12, okay? But over here, you see if it's greater than equal to 12, again, it's not in the form of less than equal to. To make it less than equal to, multiply the whole thing by -1. When you multiply by -1, you would get the same thing as above, except that everything would be having a different, their signs would toggle, okay? They would have the opposite sign, right? To make this less than equal to, you just multiply both sides by -1 and you would get this constraint. So you see that one constraint has now become two constraints. Is it clear? Both less than equal to. Yes?
Yes.
Please do not make this mistake again, okay? Now, so we do not add anything over here, okay? Please keep in mind, we are not doing simplex method. We are not doing anything right now. What we are doing now is just converting this guy into less than equal to form, okay? And it's very straightforward. The next thing is, so now we have this problem 8.3, okay? Now keep this, so this is the updated LPP so far. Okay. Okay. Now let's see how many. So this is the same as the primal problem that we started with. Okay. Let's go back here to the primal problem. I want you to count how many variables we have and how many constraints. We have x1, x2, x3. So we have 3 variables, 1, 2, 3, 4, and 4 constraints. Keep that in mind. Okay. Because in the end, when we get to the dual, we should be having 4 variables in the objective function and 3 constraints, the opposite, right? So that is a way to test whether we are in the right direction or not. Now let's look over here. 1, 2, 3, 4 variables, 1, 2, 3, 4, 5 constraints. So definitely this is not the dual, okay? Even though everything over here is now in the form of less than equal to, okay? But still, this is not in the dual form. Another thing, a question that I was asked, I just remembered, is that when you're converting this, is it okay if we have negative values on the right-hand side of the constraints? Because in simplex, if you remember, I told you they should not be negative. But when you're finding the dual, it doesn't matter. So in the dual, you can have negative values on the right-hand side. Keep that in mind, okay? Okay, unlike simplex method where we solve the problem, and I told you that you should always convert a standard form where the right-hand side should not be negative. But in the dual, while you're finding the dual, the right-hand side can be negative, all right? So with that said, now, as I told you, this is not the dual, obviously, correct? Because we do not have 3 constraints and how many, what was it, I forgot. Should be, yeah, we do not have 3 constraints and 4 variables, okay? We still have 4 variables and 5 constraints. So we have to somehow get rid of those extra variables and constraints. But this is in the standard form. So now what we have done is we have converted the given primal LPP into a standard form where we have a maximized sum objective function subject to less than equal to, okay? But this is not the dual form. Now, how do we, so once we have this, now let's see how we can get the dual, and that happens over here. Let me clear this. So it's straightforward to obtain this dual. Okay, so what will be the dual? I told you the dual now just similar to the example, the first example that we introduced. This is maximize. So we write, let me bring my pen, maximize becomes minimize, check. Okay. The right-hand side, that means these guys go into our objective function. So I have to write now, let's say our new objective function, instead of x's, we use y's. So we'll have 12y1 minus 12y2 minus 9y3 plus 10y4 minus 7y5. Okay, so you get this objective function, which is the right-hand side of the constraints in the primal. And then we take this guy, the objective function, the primal, the coefficients become the right-hand side in the dual. So -8 will be here, -5 will be here, 5 here, and 4 here. You see that? And obviously, as I told you, in the dual, if everything is less than equal to in the primal, in the dual, everything will be greater than equal to, which is also shown over here. Now, what is left is this coefficient matrix. Now, how do we get the coefficient matrix? Can you tell me, anyone? Or should I ask? How did we get this? These three, the left-hand side of the constraints in the dual. Oh, I guess I should ask.
From the previous problem?
Of course, from the previous problem, but how do I get this? So tell me, how do I get this guy? Where did this -3, -8, -7, -4 come from?
Subtracting the first and
It's
second
transpose.
equations.
Exactly, it's the
Yes.
transpose. Thank you. I just
Transpose.
wanted to make sure you guys are following or listening. So basically what I do is I take, I take these guys and the transpose. That means I put them in the row.
Yes.
4, -4, -7, 8, -3, and obviously the variables. And then I do the next and the next and the next. So I'll have 4, what is it called? Constraints, correct? And then in the end, I will write y1 to y5 greater than equal to 0. So now I have converted this standard primal into the dual. All right. Is it clear, everyone?
But here, the first, all 4 constraints, like -8, -5, 5, 4, these are like from objective function
Yes.
coefficients.
Yes.
Okay.
So these, so this, the coefficients of the objective function become the right-hand side in the constraints of the dual. Oops, that's not a good figure. This guy. Okay.
And all
Now, yes, tell me.
are greater than equal to because we are maximizing. Yes.
Yes, because in dual, as I told you, whenever I give you any primal problem, you have to first convert it into standard form. And when I say standard form or canonical form, I don't know, there are different terms for this. I call it standard form, and standard form is you should convert your problem into a maximized problem and make sure all the constraints are less than equal to form and all the decision variables are non-negative. Once I have this form, okay, then converting into dual is very straightforward. Just write minimize, multiply, take the coefficients of the objective function, put them on the right-hand side, okay? Take the right-hand side of the constraints in the primal and put them in the objective function of the dual, okay? Change the names of the variables from x's to y's, and obviously take every column in the constraint, coefficient matrix of the constraint of the primal and transpose it. That will become the coefficient matrix of your dual. That's it. But pay attention. The check is that once you do that, don't say, okay, I'm done, finished. Keep in mind that this formulation that we got is the standard form, okay? That means we may have changed the actual primal, the actual problem, LPP problem given to us in terms of number of variables and number of constraints. As you see over here, we have added some variables. Okay, I'm sorry, we did not add any variables. We have, oh yes, we have added some variables. For x2, we added x4 and x5. Okay, we changed x3 to x6, and we changed equality to 2 constraints. Okay. So in order to make sure, this is not the final answer of this, okay? This is the final answer of the standard form. But this is not the final answer of the actual primal problem that we started off with. The actual primal problem is this guy. Okay, so this is not in the standard form. You have equal to, greater than, equal to, minimized, unrestricted, okay? So I should have my dual in a form such that it corresponds to this actual original problem. That means if I have 3 variables here, 3 decision variables, I should have 3 constraints in my final dual formulation. If I have 4 constraints in my actual LPP primal, I should have 4 decision variables in my final dual, okay? So with that said, you can easily see that in spite of we converting the standard form, we still should have a lesser number of constraints and lesser number of variables, because this doesn't coincide with what the theorem tells us, okay? Is it clear? So we still have to manipulate this formulation A.4 to have how many? We should have 3 constraints and 4 decision variables. But over here, you see we have 5 y's, y1, y2, y3, y4, y5. We shouldn't be having that. We should have only y1 to y4, and we shouldn't be having 4 constraints. We should be having 3 constraints, because in our actual problem, we had only 3 decision variables. So if you remember this, again, I repeat, if there are n constraints and m decision variables in the primal, then the dual will have n decision variables and m constraints, and vice versa. Okay, so this is a checkpoint. So this is something that you have to check to make sure that the dual that you have obtained is actually corresponding to the initial primal problem that you began. Is it clear?
Yes. What if we just get rid of one?
We get rid of, I'm sorry?
Of one variable.
We cannot just get rid of that. It's not in my hand or your hand. I mean, these things, there is a logic behind it. You can't just say, okay, I don't like you, the look of you, you have so many odd numbers, I'll just remove you. No, that doesn't happen. There is a way to reduce this, and so this is exactly what I just mentioned is given over here. So we have to further refine or improve A.4 to satisfy the primal dual relationship. Okay, and now let's see how we do that. Guys, it may sound confusing in the beginning, but trust me, once you get some practice done, you will see that it's not that difficult. Only you have to know the rules, you know the rules, follow the rule set, and you're good to go. Okay, so the original problem is a minimization problem. So the dual objective should be a maximization. So, oh, we haven't, what happened? Where am I? Oh, A dot, where are we? Did we miss something? I thought we already maximized this guy. Ah, no, sorry. Okay, so we were here. We got the standard form of the primal. We converted it into a dual, okay? Now, we have to go back. So I want every one of you to write this on a piece of paper right now, so that, because I can't keep going back and forth, scrolling up and down. I want you to have this write this down right now, please. I'll give you 2 minutes. And so you'll have to refer to this every time we see what changes are made. I want everyone to write down this A.1. So this is the original problem that we started off with, the primal problem. Write it down as you see it. Okay, everyone done? Guys, everyone, you can
Yes.
just take a snapshot, or you actually have
Yes.
this on your Moodle. You should have already downloaded this lecture. Okay, so because I won't be going back, so if you see over there, the original problem was a minimized problem, right? Okay, I'll take a picture for you guys so that you guys can refer back, for me as well. Okay. So the original primal problem was a minimized problem. Do you see this? Yes?
Yes.
Yes.
Good, thank you. So that means in the dual, it should be the opposite, right? The dual is always the opposite of the primal. Okay, so if the even though you may ask me, okay, but we have already found this guy, we have converted. This is actually the standard form of the dual. But we do not want to, I do not want to see your answer in the standard form of the dual. I want you to give me in the original form of the dual after you check the number of variables and the constraints they match or not with the primal. So once we have the standard form of the dual, which is 8.4, okay, we see that this is minimized, but also in the original problem, it was a minimized, right? You see this? So this cannot be minimized. We have to change this
Yes.
to max. Hello? Yes?
Yes, yes.
Okay, we have to change this to maximize. So how do you do that? How do you change this to maximize the objective function of the dual?
Transpose.
Transpose.
Guys, how do I change this guy to maximize?
Minus
Thank you.
12
Yes.
by 1.
Multiply the objective function by -1. Simple. -1. So you get this. So now your objective function will be in the terms of maximize minus this. So you get this, okay? If you multiply by minus this, I'm sorry about my hand is shaking too much today. You get a maximize, multiply the objective function by -1, and you would get this, all right? Now, what I have done is, okay, so this is step number 1. Is everyone clear with this, why we did this? Yes or no? I want an answer quickly.
Yes.
Okay, is there anyone who doesn't understand? Please tell me so that I can repeat right now. This is the standard form of the dual that we obtained from the standard form of the primal, okay? Now we have to convert this standard form into the original dual form, which would coincide or correspond to the original problem that was given to us, which is this problem, okay? So we should be having equality greater than equal to, less than equal to, probably should be having these weird combinations in our final dual, okay? But as you see, that's not the case over here. So to do that, we have to make sure that we are in the right direction. The original problem was minimized. So obviously the dual cannot be a minimized, it should be maximized. So you convert this to maximize and multiply the objective function by -1. That's what we do over here, okay? Now, the other thing that we noticed is that there are more number of decision variables as compared to the number of constraints in the primal. In the primal, we had 4 constraints, right? 1, 2, 3, 4. So we should be having 4 decision variables, but we have 5 decision variables in the standard dual. Not good. What do? We replace 2 of the variables with another variable. So if I look at y1 and y2 over here, okay, what I can say is I take y2 minus y1 as y6, and I redefine it. So I introduce a new variable y6, which is equal to y2 minus y1, and I plug it into my equation, my standard dual that I'm trying to change. So if I do that, I would have maximize. So this whole term becomes 12y6, right? If I substitute y6 for this, and the remaining remains the same. Is it clear? So now I have got rid of one of the variables. And so now I have reduced my number of decision variables in the dual to 4, which is what I need because there are 4 constraints in my original problem. Хорошо? These 4. So there should be 4 decision variables, okay? Now let's go and see what we have over here. What have I said? Okay, and keep in mind now, since y6 is defined as the product of 2 variables, y2 and y1. So y2 and y1, as you see over here, they are non-negative, okay? So there is no guarantee that y6 will also be non-negative. y6 could be a negative value, could be 0, could be a positive value. Okay, so therefore now in my formulation, I cannot write y6 as greater than equal to 0 once I plug it into the equation. I should introduce it as unrestricted, right? Is it clear? Everyone?
Yes, yes.
Okay, so now as you see over here, I have not written anything about y6, but I've written it over here. Since y6 is defined as a difference of the 2 variables that are non-negative, okay, so now it becomes unrestricted, because depending on what values they, so if you have like 6 and this is 4, they are non-negative. Over here, y6 is equal to 2, which is okay. But if you have 4 and 6 instead, and their difference would be -2, so y6 would be negative. If we have 6 and 6, again, y6 would be 0. So it could take any range of values, and therefore it becomes unrestricted in sign. Okay? Moving on. So now what we do is, why do we replace y4? Okay, now we replace y4 by y7. I'm just trying to think why we do that. Okay. Now, we did that. Now we have 4 constraints, but we should reduce the number of constraints to 3 constraints. If you look carefully, look at constraint number 19 and 20, please. You see 19 and 20 are both greater than equal to. If I want to make this guy, okay, less than, I want to actually make this sign less than equal to, okay, and then if I do that, then I would get something greater than equal to -5, okay, and the same thing less than equal to -5. So then I could merge both of them and put it as, and replace it with an equality constraint, and that would reduce these 2 constraints to just a single constraint. Am I right? Do you agree with me?
Right.
Okay, good. Let me try to think why. Okay. So the reason why we replace y4 with -y7 is because in our original problem, the right-hand side, the coefficients are all positive. So we should maintain the sign throughout. Okay, so since over here, 10 doesn't have a negative sign, it's positive, but over here it is -10. So what we can do is we can define a new variable y7 as -y6. I'm sorry, -y4, okay? So now if I take -y4, define it by as y7, then obviously y7 would be less than equal to, and then I would be able to correct the sign of this coefficient as according to the original primal problem, okay? Now with that said, now we have 4 constraints. We have to reduce the 4 constraints to 3 constraints. To do that, let's look at equations number 23 and 24. They all have the same coefficients except for the signs, okay? So, and all of them, and they both are greater than equal to. So what I can do is I can probably multiply this guy with -1, okay? And this would become less than equal to, and the signs would then be the same on the left-hand side. And since now we have to maintain the sign of the coefficient 5 as according to, oops, sorry. as according to our original problem. Okay, so I multiplied the equation 23 by -1, and then I merge these two to become equality equation, because this has become less than equal to. The second, this guy is greater than equal to. So we know that less than equal to and greater than equal to can be merged to become an equality. And by doing so, I now have reduced the number of equations to 3. Okay. So finally, the actual dual formulation for the actual prime formulation, which was given initially, would be as such. So you can compare these two now. Let me open the other one. Okay, good. So now, as you see, let's compare. How do we compare? Okay. So as you see, let me clear off everything. The coefficients of the objective are here, and they have the same sign. Forget the equality and inequality for now, okay? There are 3 variables, so there should be 3 constraints. Check, that is right. So there are 3 constraints over here, okay? There are 4 constraints in the primal, so there should be 4 variables in the objective. Check, that is correct, okay? Now, let's see this. This is very interesting, and please pay attention to this, okay? We had one equality over here in the primal, and this equality translates to something over here. Now, I want you to tell me, what is that something? Can you guess? I told you there's always a relation between the ith constraint and the ith variable in the dual and primal. We are looking at the first constraint. Am I right? So the first constraint in the primal is equality. So therefore, the first variable in the dual, which is the first variable in the dual?
Y6.
So the first variable in the dual would always be unrestricted. This is a trick that you have to learn. So if you learn these tricks, if you're able to map this, you do not have to go through all that trouble and waste time in actually converting it to standard, then standard dual, then dual to actual this form. You can immediately, without having to do any manipulation, write the dual. And I'm telling you the trick. To understand the trick, probably you'll have to read so many books or so many pages to understand this, but I'm summarizing it for you. Okay? So I repeat myself. In the primal, you look at the first constraint. If the ith constraint, let me make it more general. If the ith constraint is equal to, then the ith decision variable in the dual would be unrestricted in sign. So this is the first constraint. So you go to the dual, look at the first variable. So constraint changes to variable, and variable changes to constraint when you want to do this mapping. First constraint, go to first variable, equality, unrestricted. Is this clear? Anyone has any question? Good. Now let's look at the second constraint. The second constraint is a greater than equal to. So what would be the second variable in the dual?
Y3.
Greater or equal to.
Is it Y3?
Well, 1 minute. That's what I was confused. Why are we writing? I wish I could have written this. Let me. 1 minute, guys. Let me just, because I should have written, like, maybe I should have changed. Okay, the notations are changed over here. Okay, now let's look at this. Let's close this, because I have written the notations. I've rewritten the notations properly in this form. Let's look here. Let's look again, just to make sure how they relate. So now what we are doing is we are trying to relate or see how the equality less than equal to or greater than equal to is reflected in the dual. Okay, so what we do is we write the actual problem and the final dual next to each other side by side, and we convert and we compare. Let's do this again. So if you have an equality, actually I've even written it over here. If you have an equality in constraint 1, this guy, in the primal, right? So you go to the first variable in this guy, which is a dot 7, which is y1. Okay, where is y1? Okay, y1 would be unrestricted as we discussed earlier. Okay, because y1 is the first variable. What I've done is I've actually just rewritten this. I made this y1, y2, y3, y4. Okay, just to make sure that the ith and ith are matching. Okay, so again, you go to the primal, the first constraint. If the ith constraint is equality, then the ith variable in the dual would be unrestricted in sign. Here, the first constraint is equality. So the first variable, which is y1, should be unrestricted in sign. So we are done with that. Okay. Now, look over here. So we see that over here, the second, okay, so vice versa. The second variable, that means x2 in the primal is unrestricted, right? So this is a variable. So we go to the constraint, second constraint. And what is the second constraint? Guys, what is the second constraint in the dual?
Equality.
So the ith variable, if the ith decision variable in the primal is unrestricted and sign, then the ith constraint in the dual will be equality. Just the opposite of what we saw for the first constraint. Is it clear? Guys, is it clear?
Yes, it's clear, Professor.
Okay.
Yes, yes.
So what we have seen so far right now is the relationship between equality and unconstrained in both dual and primal. Okay, so this is important. Okay, so if you learn these tricks, then it's very easy. If any quiz or anything, you can quickly just do it without wasting time. Okay. Now, before we continue, I would like to make something very clear to everyone. And the thing is that when you're given an LPP problem or LP problem, it is always desirable. That means we would always like to see or convert our problem into a form where the objective function is maximized, okay? And it is always desirable to have the constraints in the form of less than equal to type. Okay, that's what we saw in our example. Any problem, we first converted it into a problem which we call the standard form, where the objective function was maximized and all the constraints were less than equal to. Okay, why is it so? Because it becomes very easy to convert any problem, any LP problem in this standard form to its dual. Okay, now the question is, okay, what if I have a primal problem, LPP problem, where the objective function is minimized and the what is it? Constraints are all greater than equal to. That's also good. That's easy. Okay. The problem occurs when we have a mixture of inequality and equality constraints. So what are the desirable cases? So if I want to do this matching, this simple matching without having to go through all those conversions, what is the simple cases? So I would always want to see. So you may ask me, okay, but this guy over here isn't minimized. What's your take on this? I would say yes. So the desirable conditions are when the primal is, so if the, let me put it in this way, if the primal is maximized, we would like to see all the constraints in the form of less than equal. If the primal is minimized, we would like to see all the constraints in the form of greater than equal. Okay, so if I give you a problem like this, convert it first either to in this form or in this form. I'm not saying it should always be maximized. I mean, the reason why I'm using maximize is because it's easier to follow, because we have studied the standard form. Even if you convert it to minimize, but you make all the constraints greater than equal to, it's okay. You can easily map it to its dual using this trick. Okay, so let's put it this way, finalize it. The desirable condition for a primal LPP problem is to either be in a maximize object, a maximize form, and all the constraints are in the form of less than equal to, or minimize and all the constraints are greater than equal to. Is it clear? If you agree, or if you make sure that
Yes.
the problem is in such a form, then we have no problem in actually solving this problem, in converting the dual or finding it immediately. Okay. So let's see. Now it's saying that our problem, which was the initial problem, so it is minimized. Okay. So as I said, if so, look at point number 3. It says that since problem A.1 is a minimization problem, so I said minimize means the constraints should always be greater than equal to. So that means these two constraints, that means constraints greater than are good, desirable. These two guys are not what we want, and so we should somehow change them into greater than equal to. All right? Is it clear? That's what this point is saying. Now, why do we make this point? Okay. Now, we got rid of these 2 points. So these 2 points are the first constraint, first variable, a second variable, second constraint. So we got rid of this guy. 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 All right. Is it clear? We learned about this. Now, what I'm trying to say is this. This was a minimized problem originally. So the desirable constraint form would be of the form this and this. So let's look at the second constraint. The second constraint is desirable. That means it's in the form of greater than equal to, because it is a minimization problem. Okay. So if this is in the, if the ith constraint is in the desirable form, depending on whether it's minimize or maximize, okay, then the corresponding ith variable in the dual will also be in the desirable form. So what is the desirable form? Greater than equal to 0. We always want everything to be greater than equal to 0, no matter whether it's primal or dual. Okay. So this is greater than equal. So the second constraint in the primal is desirable. This means that the second variable in the dual should also be desirable. So y2 should be greater than equal to 0. Is it clear, everyone?
Yes.
Okay.
Yes, yes.
So you can say the same thing about this guy, right? Let me write, so we did this and we are done with this. This guy is also in the desirable form because it's a minimize. So the fourth constraint is desirable. That means the fourth variable should also be desirable. Check, cancel. You have checked this. This is how you check whether your dual is actually correct or not, okay? Now, let's go to the undesirable cases. It's minimized, so we do not want to see equality. We do not want to see less than equal to. We already deal with equality separately. Now we have a less than equal to. So this guy is remaining. The third constraint is undesirable, and therefore the third variable should be undesirable in the dual. Undesirable means we do not like less than equal to. Undesirable is the opposite of desirable, so if less than equal to 0 is not what we desire. So we see that there is a match between these two as well. So we cancel this and we cancel this. Correct? Let's go here to the dual. It's a maximized problem. So everything should be in the form of less than equal to. So the first constraint is desirable. Therefore, the first variable in the primal should be desirable. Check. Check. So we have already dealt with equality because we have canceled it. This guy remains untouched. So now let's see. This is an undesirable case. So I mean form, right? It's greater than equal to. We desire to see less than equal to for a maximization. So since it's greater than equal to, this is undesirable. Therefore, and this is the third constraint. So the third variable in the primal will also be undesirable. Check. And now I can confirm that this is actual. This is actually the right dual for my original primal problem. Is it clear? It may be difficult or maybe mind-boggling a bit in the beginning, but once you read through and you actually imagine the connections between them, it would be very easy to help you in your exam to quickly convert. So in your exam, I may ask you, okay, I'll give you a primal problem. I say solve the simplex of its dual. That means I want the dual from you and I want to see the solution of the dual, even though maybe the dual and the primal give you the same solution. I don't care. I want you to solve the dual. That means you have to obtain the dual first. You can either write the primal. first convert it into the standard form, then convert it into standard dual form, and then get this, which is a long process. Or by learning this little trick, you can come and checking it, of course, you can get the dual immediately and just solve this dual. Is it clear, guys? So just to summarize everything and put everything in perspective, this is how you would convert it. If you have your primal, and assuming that the primal is max, okay, and the dual would be obviously min. It doesn't mean that the primal should always be max. Let me write it in red. If your primal is min and you have these conditions, these same conditions, then the dual should be max and the same conditions. It doesn't mean that you should always have max and min, max as primal and min as dual. No, there's no such thing. All right. So let's assume that the primal is max and you have the number of constraints. So the number of constraints would become number of variables. If there are n constraints in the dual, we should be having n variables. If there are m variables in the primal, there should be m constraints in the dual. The right-hand side of the primal becomes the objective function in the dual, and vice versa over here. The coefficient matrix is transposed. Equality signs become unrestricted. Remember, we just saw it. So if you have an equality sign in the primal, it will become, so the ith equality constraint will become, will correspond to the ith variable in the dual to be unrestricted in sign, okay? And vice versa. If you have unrestricted variable, the ith unrestricted variable in the primal will become, will correspond with the ith constraint, which is equality constraint in the dual. So this, if it's a max, desirable means less than equal to, and desirable variable means greater than equal to variable, okay? This is undesirable, so greater than equal to constraint would become less than equal to variable, okay? Greater than equal to variable, which is desirable, okay? It's a variable, not constraint, okay? That means it will become greater than equal to constraint in the dual, and same for the less than equal. So if you learn this, this is all you need to know. Converting between this is very easy. Another thing that you should know is that if you have a primal, you obtain the dual, and I ask you what is the dual of the dual, what would your answer be? I give you a primal problem. I ask you to find its dual. Okay, now I ask you to find the dual of the dual. What is this dual?
Primal?
Exactly, it would be the same as primal. Okay, so what I'm trying to say is the dual of a dual is a primal. Okay. I guess we, oh wow, 1:30 almost. I'm sorry to keep you guys. I lost track of time. We will stop over here. In our next class, we will look at these three. There are 4 theorems actually, and I would discuss that. That's very important. And after that, you have the supplementary, which are solving some exercises. I expect you to do it. And next week, you'll be having a quiz on Tuesday, okay? And the quiz will be on only the duality. That means lecture 7 and 7 supplementary, okay? So please prepare for it, practice properly,
Okay.
and yes?
No, okay.
Yes. So next Tuesday, you'll be having a quiz on duality. So study well. If you have any questions, please ask me on Thursday. Do we have any questions so far?
No questions.
Okay.
No question.
Thank you, guys. Study well and take care of yourself. See you on Thursday.
Thank you. Bye.
See you. Bye-bye.
Goodbye.
Bye-bye.